Fourier transform and numerical tools. So this presentation is divided in two parts. The first part I will give a brief explanation about Wavelet transform. And the next part will give an introduction to the numerical tools by showing some examples, applications. Start from the Fourier transform. It's a mathematical form of Fourier transform. So intuitively, just project the signal onto a sinusoid function domain. It means we use a set of scaled sine waves to return the original signal. Like we choose a particular frequency sine wave and multiply by the original signal and do an integration. Get a result. If the result is non-zero, you can say the original signal have this frequency component, and then we continuously change the scale, change the frequency. You can get the frequency spectrum of the original signal. So Fourier transform just maps the signal from time domain to frequency domain, drops all the time domain information. It has a higher frequency resolution. So, but if the input signal has some frequency sharp change, like a break point at some time, although in the frequency spectrum we can see some high frequency component, but we don't know when does the break point happens. So it's only suitable for stable signals. However, in real world, there's not too much stable signals. Stable signals are generated by people. And almost all the signals are varying along times. So to analyze the unstable signal, we have the continuous Wavelet transform. The top formula is the mathematical form of Wavelet transform. Actually, it's a headache to me. So like the Fourier transform, it just projects the signal into a small wave domain. We change the base function from a sine wave to a small wave, from infinitely long sine wave to an oscillating small wave. And since it is a small wave, so we call it Wavelet transform. Like we did in the Fourier transform. For the Wavelet transform, we just choose a scale factor. Say the formula, it has two parameters. A is the scale factor and B is the translation factor. So to do a Wavelet transform, we choose a scale factor and do a convolution with the input signal. Then we get a result with a function with respect to the translation factor. So, and the scale factor can be treated as a kind of frequency, and the translation factor is kind of time. So it has a time and frequency representation, and better time resolution of higher frequency, and better frequency resolution of lower frequencies. So why this has this property? Say if we choose set a larger scale value, and that means the small wave involves some high frequency component. And during the convolution, we shift this small wave along the time axis and multiply by the original signal. We can capture the high frequency components of the original signal and also record where does this high frequency component exist. So it has a better time resolution of higher frequencies. For lower frequencies, we just decrease the scale factor. It has expand the scale small wave, so it has some lower frequency component. So it can record all the low frequency components. Since in real world, some useful information really exists in low frequency band, so it has a better frequency resolution of lower frequencies. But say the math form, if the input signal is 1D, but we can get a 2 two-dimensional result. So it involves highly redundant information. However, like the fast Fourier transform, there is also fast Wavelet transform to effectively compute the Wavelet transform of a signal and analysis. So here's a basic form of the fast Wavelet transform. Generally, it's basically just a cascaded filter bank, and each filter bank is involves a high-pass filter and a low-pass filter, followed by a two-fold downsampling. It's a basic form of fast Wavelet transform, and for each high-pass filter, it will produce a result, and the final wavelet coefficient is just calculated to the result of high-pass filter, the last low-pass filter, but in a reverse order. So you can say the result of the last low-pass filter comes first. So this coefficient involves all the low-frequency band information, but the D1 involves all the high-frequency band information. And so let's say say in frequency domain, if the input signal has this frequency spectrum, the Wavelet transform is just first we apply a filter bank, high pass and low pass filter. So this part is D1, and subdivide the frequency band again. So this is D2, and repeat the process D3 and D4. Okay. So that's a frequency domain information, but the Wavelet transform is doing in time domain. So suppose the input signal Xn has a length of 258, and the D1 is 128, and D2 is length of 64, and D3 and D4 is 32. So for high frequency information, it has more sampling, so it has a good time resolution and involves all the high frequency information. But for the lower frequency band, although it has less samplings, but it involves almost all the useful frequency information. So it has a better frequency resolution. Okay, let's see a real example. The top figure is a input signal. Can you see it? Maybe it's too light. That's the top figure is the input signal. This figure is a Wavelet transform. This figure is a Fourier transform. Okay, let's say the Wavelet transform just we apply two cascaded filter banks. There's only D1, D2, and so D4 is gone. Here's D3. So D3 is the output of the low-pass filter. So the result is divided into three parts. This is D1, this is D2, and this is D3. So we can say only the high frequency part, it only contains those peaks, and in the low frequency part, since it contains all the frequency components, so it has the same shape with the input signal. And in the high frequency part, say those peaks, because it has a good time resolution, so those peaks are corresponding to the breakpoint of the original signal. And say the Fourier transform, although we can extract all the frequency information, but that doesn't make sense to us because in the original signal it has many breakpoints, but we don't know where does those breakpoints exist, seen from the frequency spectrum. The 2D Wavelet transform, the Wavelet transform for images has a similar structure. We just apply the 1D Wavelet transform along each column and each row respectively. because the structure is more complicated. So let's walk through the process. First, we apply a high-pass and filter along each row and high-pass filter along each column. So we get a high-pass information along each row and the column. So we get all the high-frequency information and store in the D diagonal as a submatrix. And then we apply high-pass filter to each row and low-pass filter to each column. Then we extract the high-frequency information along each column, along each row horizontally. And then we do a low-pass filter to each row and high-pass filter to each column. And we got the information along each column vertically. And last is a low-pass filter to each row and column. And we get the low-frequency information stored in the D basic matrix. And the wavelet coefficient is composed of those four matrices. So it's maybe boring to see this diagram. This is a real example. So suppose we have a figure. We want to do a wavelet transform. Maybe you all know this lady. So that's a wavelet transform of the input image. So this is the basic information, the basic frequency information of the input image. And this part is a horizontal details, the horizontal, and this part is the vertical details, the vertical. And this is a high frequency information along each row and column, so the diagonal. So that's an example of a wavelet transform, a 2D wavelet transform. And the similar structure can also apply to 3D information, but it's become much more complicated, so I didn't show it here. Next, I'm going to introduce the numerical tools of data science. So basically, it's just a collection of numerical computation tools. So it is also a tutorial over some modern data science algorithms and methods. It covers signal processing, machine learning, computer vision, and computer graphics, and so on. So it also provides a lot of applications, the applications of wavelet transform and mesh processing algorithms, which I think is very useful to us. Also, there's some implementation in MATLAB, Python, R, and Julia. Although our research group using C++, I think it can be used to test your algorithm and verify the result. So for the wavelet transform part, I think its key implementation is actually implements those two wavelet transform functions. The first wavelet transform is for 1D and 2D data. That's 4 parameters. The X is the input data length. It can be 1D or 2D. Input data, it can be 1D and 2D. The length should be a power of 2. The second parameter determines the wavelet transform levels. It means how many filter banks is cascaded. Let's go back to the structure. So since it's a cascaded filter banks, the performed wavelet transform is implemented as a recursive function, and the parameter j should satisfy the condition. It's also the terminate condition for the recursive function. If you give a larger j value, and if the input data length is smaller than after a log, if the length is smaller than j, then the recursive function determines terminated, and the wavelet stop right there. So we got a less level wavelet transform. So the third parameter is the direction. Means so it can be +1 or -1. It means we can do a wavelet transform or inverse wavelet transform. And the second important function is the perform Wavelet mesh transform. It can do Wavelet transform over mesh, so it has more input parameters like the vertices, faces, and the function. The function is just a function defined on the input mesh, or it can be the mesh itself. It can be the geometry of the mesh. Sorry. And the last two parameters are similar as the Wavelet 1D and 2D Wavelet transform. So let's say some real application. This application is the image approximation. So first we do a Wavelet transform to the input image and drop 90% of the Wavelet coefficient. So remember the Wavelet coefficient has the same size of the input data. So that means we compress the original image. Here we got a 10-to-1 compression. So let's run the code. Let's see the code first. So this is just load the data and perform a Wavelet transform. So here J is equal to 0, so we want to do as much as Wavelet transform as possible. Now it perform thresholding. Here we just pick the 10% largest data. We do a hard thresholding and then reconstruct the image to see if we can recover the image. That's right. Okay. And say maybe the approximated image looks better than the original image because some high frequency noise also removed. Let's move to the next example. It's an approximation of function defined on mesh. It's a 3D Wavelet transform. So just reconstruct the function. The function is just like the color information over the sphere. Reconstruct the function by using only 20% of the Wavelet coefficient. Get a 5-to-1 conversion. Let's see the code. So those are loading data and do some configuration. This is a function defined on the mesh. That's a color information on the mesh. And then we perform a Wavelet transform, do a hard thresholding, drop 80% data. Drop 90%, 80% data, and do a hard thresholding and reconstruct the mesh. Run the code. And plot the result. See, the color information are almost all preserved, except some darker pixels, because those dark pixels can be treated as some high frequency component. So since we do a hard thresholding, those are removed. Just the dark pixels is removed, but all the basic information is preserved. We only use 20% of the input data. The last example is a Wavelet transform over the mesh surface. It's also an approximation. So let's check out the code. So first load the data bunny and do some configuration for representation. And next set the function to be the mesh vertices itself, the geometry information, and then we do a Wavelet mesh transform. And then compression, drop 90% of the Wavelet coefficient, and then perform inverse Wavelet transform. Gonna take a long time. Okay. See, although we lost some details, but the basic bunny is we can still recognize that it is a bunny. It's hard to use. Okay. So there's also some other applications of Wavelet transform, like the Wavelet denoising, Wavelet watermarking. But they all use the basic Wavelet transform as introduced here. So if you are interested in those applications and some other applications, you can refer to their official website, numericaltools.com. I'm going to this website. Okay. That's it. Have any questions?
I have questions. I'm just wondering. I know Wavelet transform will do a downsampling by number 2.
Yeah.
And so why is number 2? I'm just.
It's proven to be the most effective factor.
So number 2 is just most effective way to do downsampling. Okay.
That's I think.
And the next question is.
I could be wrong.
Okay. So next question is still about the number 2, and you said the function should be a number power of 2.
Well, that's just the implementation.
So when you play implementation, you must the function must be a number
should be
power of 2. So what happens if it is not? So we cannot always guarantee it is always.
Give you some error. You have to first process the input data. Drop some point.
Drop out some part. Okay.
You can have Wavelet transforms, by the way, that have factors other than 2, but
Yeah.
2 is the most popular, just because 2 is the small. Well, if you choose 1, it doesn't do anything.
Yeah, that's true.
So 2 is like kind of the simplest number you can pick. So it's been more kind of rigorously studied theoretically, knowing people know the properties. It's probably easier to design Wavelet filter banks with just 2 channels. So, but you could have more than 2. It's just they're less popular.
Okay.
About the Wavelet transform, you applied the Wavelet transform over the meshes, right? Like the 3D meshes, like the bunny. Did you use the mesh to apply the Wavelet transform for this example, for example? So what was the type of your input mesh? It was OFF5?
It should be a semi-regular mesh.
What is that?
That means like suppose the bunny is composed of triangles, right?
Yeah.
So every triangle should be the same.
I mean, so it's a different format than .OFF5?
Oh, you mean the format?
Yeah.
Format doesn't matter. So I didn't check out the input format. So you can implement the function to accept other formats. So I just load the original data in that package.
Yeah.
So I'm not quite familiar with MATLAB, so I don't know which format is supported.
Oh, so the input mesh file is already provided in the MATLAB for the bunny?
Yeah. So you can see here, I just read the data, load the data.
Okay.
This would be an important thing to figure out, because like this is basically kind of the starting point for his project. He's going to be doing stuff related to like wavelet transforms for meshes, so you kind of need to know for sure like what the format is, because the idea is you can use this code to sort of test and make sure that your code that you write is working. Maybe you just want to interject something here, kind of an important comment, but not really necessarily a suggestion for improvement of the presentation, but just there was maybe a misunderstanding a bit about what the scope of the presentation was meant to be. Like you presented really just like traditional wavelet transforms, like for like what you covered in 586 course. I think everyone took wavelets in 586, right? But the purpose of the presentation was to talk specifically about only the mesh case. And the mesh case you completely ignored, except for the demo. But the whole point really was to explain to people, because I think everyone here, you may have forgotten some of what you learned, so it could be a good maybe exercise to relearn some of the stuff you learned before. But the intention was to have you cover just kind of exclusively the mesh case, because that would be new to everyone. Because it's a totally different deal how, I mean, you can't apply a filter bank to a polygon mesh. It doesn't work. It's like a different, it follows a similar pattern, but it's different. And maybe to just make one comment about semi-regular meshes. Semi-regular mesh, if you look at wavelets, you all know subdivision from 586. Wavelet transforms are like running subdivision backwards. So instead of you're adding more and more vertices and faces, you're starting with the mesh and you're removing them. But in order to remove them, they must have had the topology that they were generated by subdivision. When you run subdivision,